Section 5, Sketching Curve. I'm your host, Dr. D. Missed. We'll edit that out later. Okay, sketching curves. We're basically putting everything together that we've learned, including some stuff we've learned in Algebra 2 and math analysis. So here are the things that we're going to be thinking about when we see a function that we want to graph. We're way past simply plugging in x's and trying to find y's. We want to know the shape of the curve due to all of the things that we've been studying. So first thing we want to look at is the domain of the function. In other words, what x values are defined and what x values are not defined. If I have y equals the square root of x, I know not to even bother trying negative numbers because anything under the radical has to be positive. So domain is the first thing we're looking at. Next thing, x and y intercepts. Those are pretty simple to get, so we want to do those very first thing, and that is you plug in 0 for y and find out what x is, or basically set the function equal to 0 and solve for x. That's your x-intercepts. Now the y-intercept's even simpler. Plug in 0 for x and find out what your function equals. Now, next thing we're interested in is symmetry. If we realize that f of negative x equals f of x. In other words, if I put a negative value in for x and I get a positive y value, then that means, or basically I change the sign of the x and it does not change the sign of the y, then that means this is an even function. And if it's even, it means it's symmetrical about the y-axis. So an example, that would be a parabola. If I have y equals x squared, now if I put in a negative 2 or a positive 2, that doesn't change anything for y. So that makes this an even function, and that means whatever is left of the y-axis is the same thing as what's right of the y-axis. That cuts our work in half. We only have to do half the work and then just rewrite it on the other side of the y-axis. Or y equal cosine x. That's another even function because you know the cosine function looks like this. So whatever's right of the y-axis, same thing as what's left of the y-axis. Those are even functions. Now, if f of negative x equals negative f of x, then we have an odd function, and that's going to be symmetrical about the origin. An example there would be y equals x cubed. If I flip that thing upside down, it ends up being the same thing. Or if I put in a negative value for x, I end up with a negative y. So here, if I put in a 2, then y is going to be 8. But if I put in a negative 2, y will be negative 8. Another example of an odd function would be y equals sine x. Because notice, if I graph y equals sine x, okay, now this, if I rotate it 180, it ends up lining up with itself, and it will be the same function. If I put in a negative value for x, I end up with a negative y value. So even functions and odd functions cut your work in half because all you have to do is do half of it and then you know what the other half is. Now, the other type of symmetry would be periodic. And once again, a trig function is a good example of that. If I draw one period, then I know all the rest of the periods So I only have to draw one period, I'm good to go. So that's a handy shortcut to know when you're graphing if there's symmetry, because it cuts down your work. Okay, next, asymptotes. Now asymptotes are vertical or horizontal. Now when we're talking vertical asymptotes, that's basically x values that the function is undefined. Well, we flushed those out when we did the domain. When we found out what was undefined, then we found out the vertical asymptotes. For example, if I have y equals 1 over x, I know my vertical asymptotes are going to be x equals 0. Now, the horizontal asymptotes are what the function does when x approaches infinity or x approaches negative infinity. In other words, where is the function going to settle out if I go indefinitely to the right or to the left? Those are going to be horizontal asymptotes. Now remember, vertical asymptotes, the function is undefined on that asymptote, on that x value. But horizontal asymptotes, the function could be defined several times on the horizontal asymptote. It's basically saying that's what the function levels off to, way to the right or way to the left. So horizontal asymptotes would be the limit as x approaches infinity of f of x. That's going to be some y value that's going to be the horizontal asymptote. Or the limit as x approaches negative infinity of f of x is also going to be some L value or some y value, and it could be a different y value. You could have a horizontal asymptote in the positive direction and in the negative direction that, like logistic growth functions, would have different asymptotes going to the right and the left. So that's going to give us a clue of how to graph it if we know where it's going to end up if we go indefinitely to the right, to the left, up, or down. Now notice if I let x approach infinity here, then y approaches 0, which means this function will level off to y equals 0 if I go indefinitely to the right and to the left also. So I know that function is going to end up looking like this. So notice I have a vertical asymptote at x equals 0, and I've got a horizontal asymptote at x equals, or at y equals 0 also. All right, now, next is where we get into the calculus. Intervals of increase and decrease. Well, how do we know? Last section we did that. Just take the first derivative. Wherever the first derivative is positive, we've got increase, and wherever the first derivative is negative, we've got decrease. So that means you know if the function is going downhill or if the function is going, downhill again, or if the function is going uphill. Now, tied in with that is relative maxes and mins. Now, the relative maxes and mins are where the first derivative equals 0. So you take the derivative, set it equals 0, solve for the x's. Now remember, those x values are not the maxes and the mins. They're merely the location of the maxes and the mins. To get the actual maxes and mins, you plug those x values back into the function, and now you've got the maxes and mins. Now, after we have maxes and the mins, it's also handy to get the concavity, which means second derivative. Now, where the second derivative is positive, the curve is opening, or the concavity is up. And where the second derivative is negative, the concavity is down. And where we have change in concavity, we have a point of inflection. That means where it's going from concave up to concave down, if it's continuous, then we have a point of inflection there. Now notice, in this example, y equals 1 over x, the change in concavity is at y, or at x equals 0. And that's not continuous there, so you don't have a point of inflection there. Okay, so you guys know all this stuff already, especially considering the quality of instruction you've received in math analysis and back to algebra 2. So let's just do some of these. Look out. Oh man, that was a close one. Yeah, that's all I got to do is trip over the cord and pull down the camera, and then you guys be looking at the floor while I continue talking. All right, so back to the ranch. Okay. So let's try graphing y equals 2x squared over x squared minus 1. Okay, so we're going to just go through that checklist that I just gave you for functions. First thing we want to look at is the domain. What x values make this thing defined? Well, basically, what x values make it undefined would be wherever the denominator is 0. So where is that going to be? That's going to be where x squared minus 1 equals 0. That means where x squared equals 1, and that's where x equals plus or minus the square root of 1, which would be plus or minus 1. This is where it's undefined. Now that means we can say that the function is defined everywhere else. So if I mark those asymptotes, okay, x equals plus or minus 1. That one became a little too big. Okay. There is where the function is undefined and it's defined everywhere else. Okay, next, let's look at the intercepts. So the easiest intercept is going to be when I put in 0 for x. So I end up with 0 over negative 1, which is 0. So that means I have a point at 0, 0. Now the y-intercepts, if I let y equal 0, then basically 2x squared over x squared minus 1 equals 0. That means 2x squared equals 0. That means x equals plus or minus 0. So 0, 0, that's it. We've got both x and y intercepts all in that one point. Now, next, we want to look at the symmetry. Make sure I'm not forgetting something. Yeah, right. That's it. Symmetry next. All right. Now, look at the function and think about if I put in a negative value for x, what's going to happen to y? Well, that's the same thing as the lyrical answer, or I should say, the answer to the lyrical question, war, what is it good for? Absolutely nothing. So if I put in a negative number for x, I end up with the same y value because every single x value is squared. That means it's an even function, and that means it's symmetrical about the y-axis. So basically, if I just focus on everything to the right, then everything to the left just gets copied. Okay, well that's handy. So next, we're going to look at the asymptotes. Now, we just got the vertical asymptotes here. Now, the horizontal asymptotes, if I let x approach infinity, what happens? Well, notice I have 2 times infinity squared over infinity squared minus 1. Now, that basically is going to approach 2. If you remember from Algebra 2, if the degree of the numerator and denominator are the same, then it's just the ratio of lead coefficients, which is 2 over 1. So that means I've got horizontal asymptotes at x equals 2. And remember, we just said that the symmetry about the y-axis, so clearly whatever's right is left. So the horizontal asymptote is y equals 2 for anything. Okay, now back in Algebra 2, we would just say, okay, let's just start plugging in x values, and we'll take x values to the right of 1, and then in between -1 and 1, and then we just connect the dots. But we're a lot more sophisticated now than we were back your sophomore year in Algebra 2. So now we're going to say, let's find where this function increases and where it decreases. So, time to take the derivative. And we've got, let's get these back in black. Okay, so the derivative, we need the quotient rule. So we've got y prime equals low d high minus high d low square the bottom. And away we go. All right, so here's our first derivative. And that's actually going to equal let's see, 4x cubed minus 1. Oops, 4x cubed minus 4x. 4x cubed minus 4x minus 4x cubed. Okay, so 4x cubed minus 4x cubed is just going to be a minus 4x. So let's just save a little time here and just go, okay, that's minus 4x over x squared minus 1 squared. All right, what did that tell us? Well, that told us that the derivative is positive whenever x is negative, and it's negative whenever x is positive. So basically, if we just look where x is positive, that means this function is increasing everything to the right of the y-axis. Y is increasing, just write this down, y is increasing to the right of the y-axis. Okay, now, while we have the first derivative, let's see where we have maxes and mins. So we set the first derivative equal to 0. Now, anytime you have a fraction equals 0, then the numerator is all that matters, because the denominator cannot make this fraction equal to 0. But if x equals 0, then the whole fraction equals 0. So that means at 0, 0, remember where x equals 0, y equals 0. So, oops, what am I doing? So at 0, 0, we have a critical point. Now, what kind of critical point is that? Well, if I go, let's see, yeah, let's do it like this. If I go to the left of 0, 0, then the derivative ends up being positive. Notice the bottom is always positive. So if I go left, the derivative is always positive. So that means it's increasing to the left and it's decreasing I wrote this incorrectly. Y is increasing to the left of the y-axis. And it's decreasing to the right. Okay, so that means at 0, 0, I have a point of inflection because I don't have a change in the first derivative at that point. In other words, it's not going from a positive slope to a negative slope or a negative slope to a positive slope. So this is not a min or a max. It has to be a point of inflection because it's going from a positive slope, it's increasing. Yeah, it's increasing to the right and decreasing. Oh, come on. Okay, it has to be a max because it's increasing to the left and then when it gets to 0, it begins to decrease. So that means it has to be a maximum at 0, 0. So the point 0, 0 is a relative max. Increasing to the left, decreasing to the right. Yeah, so you have a max at 0, 0. Okay, now, the last thing we need is concavity. So concavity means we need the second derivative. So we're going to take the second derivative of the function, and let's just make sure, yeah, okay. So y double prime is going to be the derivative of y prime. So I go low d high minus high d low. Okay, now notice the derivative of the bottom is going to be 2 times x squared minus 1 to the first power. And we've got see, x squared minus 1 is a function, so we have to take the derivative of the inside, which is 2x. So, low d high minus high d low, square the bottom, and away we go. Okay, so let's clean this up now. So we've got -4. You know, here's what we'll do. I'm just going to do this in my head. It comes out 12x squared plus 4 over x squared minus 1 cubed. Now you can do that on your own and just make sure I did it right, but that's what I'm seeing. So Now, this is the second derivative. What we want to know is, where is this second derivative positive and where is it negative? Well, notice if I'm going to the left, yeah, what I have to do is I have to do 3 separate sections here. And let's just do this. Clear some stuff out of here. Okay. All right, so the second derivative, 12x squared plus 4. Notice the numerator is always positive. No matter what I put in for x, positive or negative, I'm squaring it so it's positive. And I'm multiplying by 12 and adding 4, so the numerator is always positive. Now, where is the denominator going to be positive or negative? Well, if x is less than negative 1, then that means I'm squaring a number that's a greater negative than 1. That means I have a positive number bigger than 1. When I subtract 1, I get a positive number, cubed. So that means what we found out is, to the left of negative 1, we have concave up. Now, in between negative 1 and positive 1, when I square that number, I'm going to have a number less than 1. Now, if it's less than 1 and I subtract 1, that means I have a negative number. Cubed makes it negative. Top's positive, bottom's negative. That means it's concave down in between negative 1 and 1. Now, if I put in a number greater than 1, I square it, subtract 1, that's going to be positive. So I have concave up again to the right of positive 1. All right, so let's summarize what we have here. I'm going to have to rewrite that. Okay, so we have our horizontal asymptote at y equals 2. We have our vertical asymptote, or asymptotes, at x equals negative 1, x equals positive 1. Let's continue this out here. And we've got our relative max at 0, 0, which is our x and y intercept, the only x and y intercept. And so now we're ready to actually graph the curve. So let's do that. All right, so okay. Now, notice the curve is concave up until we get to our asymptote here at x equals negative 1. It's concave down in between negative 1 and positive 1. And it's concave up between 1 and infinity. It's defined everywhere except at negative 1 and positive 1. It has horizontal asymptotes at y equals 2. And so basically the only points I would have to go, oh, and yeah, that's all we did. It has only one relative maximum and no relative minimums here because it continues to get smaller and smaller, or closer and closer to y equals 2 as we go right and left. So basically the only thing we would have to do now to confirm everything is maybe plug a point in at x equals 2 and x equals 5. And then I don't even have to do anything on the left because I know whatever's on the right is on the left. So basically if I plug in 1 or 2 points here, then I have the entire curve. So that's it, game over. All right, you're going to find that most of the work in this section is going to be exactly like we just went over. I'm just going to do one more example problem. There's nothing like doing this on your own. Like, you could watch me do it over and over, but really, you got to get in there and do it yourself. But the key thing you have to remember when you're doing this is back to, oops, wrong way. Back to this list. You simply have to think through each thing, and the more you do it, the easier it gets. Looking where the function is defined, where it crosses the intercepts. Symmetry cuts down your work. Asymptotes show you where the function's going as you go right, left, and where it's going to approach up and down also. Intervals of increase and decrease, relative max and mins go hand in hand with first derivative, and then the second derivative will show you the concavity and points of inflection. So, piece of cake. Like I said, let's do one more example. Let's try, yeah, I like example 2. That's kind of handy. Now you could go through the other examples in the book on your own because they are really pretty simple, but if we take, we just had a rational function. Let's do example 3, xe to the x. So let's try that. Okay. Y equals xe to the x. Now, first of all, where is the domain of this function? Well, what restricts the domain is radicals, no radicals there, or, and I should say even indexed radicals. So square roots, fourth roots, sixth roots, because cube root doesn't restrict the domain. You could have a negative cube root. So radicals, and secondly, fractions. There is no fraction, so there's no place to have a 0 in the denominator. So there is no restriction on the domain. Now, yeah, I was going to say when you have e to the x, you could have a restriction on the range, but because you have x times e to the x, there's no restriction on the range either. So we've got basically nothing there. So intercepts. If I let x equals 0, then y equals 0 once again. So that means I have the point 0, 0. And if xe to the x equals 0, the only x value could be is 0. So that's it. There's my y and x intercepts. So next I want to check symmetry. Well, if I put in a negative number for x, then I've got a negative y value. And if I put in a positive number for x, I have a positive y value, except for the fact that e to the negative x will not be the same numeric value as e to the positive x, so there is no symmetry at all. In other words, let's check this out. If I put in a 2, so y, come on. Yeah, y equals 2 times e to the 2. Now if I put in a negative 2, I get y equals negative 2e to the negative 2. Well, notice this equals negative 2 over e to the 2. So they're not the same value. 2e squared or negative 2 divided by e squared, two different things. So we have no symmetry. It's neither even nor odd. So there is no symmetry. It's not periodic either because it's an exponential function. So no such help from our symmetry. Okay, so next we want to check on the increase and decrease so we can find out our first derivative to get that. So we go y prime equals first times derivative of the second plus second times derivative of the first. So that equals e to the x times the quantity x plus 1. That's our first derivative. Now, if we set that equal to 0, let's just for notation, convenience of notation here, we're going to call this f of x. So f prime of x equals e to the x times the quantity x plus 1. So now, if x is positive, then I've got a positive times a positive, which is positive. If x is negative, well, let's say if x is less than negative 1, I've got e to whatever power is always positive. So if x is less than negative 1, suddenly this derivative is negative. So that means if for x less than negative 1, f of x is decreasing. And for x greater than negative 1, f of x is increasing. So that means for x equals negative 1, the first derivative equals 0. So that means if you have the first derivative, the first derivative equals 0, and the function is decreasing beforehand and increasing afterward, then that makes your derivative, or that means your x equals negative 1 is a relative max, or relative mean, decreasing to increasing. So, yeah, that means x equals negative 1 is a relative min. All right, now what is the relative min? Well, I need to put in negative 1 in here, and it becomes negative 1 times e to the negative 1. That would be negative 1 over e. So negative 1 over e is my relative min. And so let's put that on there. Where is negative 1? Yeah, we don't have a decimal approximation there. All right, let's check that out. So negative 1 over e is going to be 0.367, so approximately 0.4. All right, so at negative 1, negative 0.4. We've got a relative mean. And now let's check concavity, and then we'll be ready to go with the graph. So concavity, we have to take the derivative of the derivative. So f double prime of x equals the derivative here. So it's first times derivative of the second plus second times derivative of the first. So that equals e to the x times the quantity x plus 1 plus 1. So the second derivative is e to the x times x plus 2. Now, once again, e to the x is always positive. So that means at x less than negative 2, we've got a negative second derivative. What's that mean? That means it's concave down. At x equal negative 2, we've got a change in concavity. So that means we've got a point of inflection there. And at x greater than negative 2, we've got a positive second derivative. So that means we've got concave up. Okay, so if I plug in x equals negative 2 into my function, then I've got f of negative 2 equals negative 2 e to the negative 2, or negative 2 over e squared. And that equals negative 0.27067. So that's approximately negative 0.3. Okay, so that's our point of inflection. So negative 2 and negative 0.3. Point of inflection. And like we said, it's concave down to the left and concave up to the right. So let's get rid of this stuff now. Okay, so we've got concave down here. And we've got concave up over here. And we know we've got a relative min, so we know it's going to go up like this, and then it's going to go, it's got to go concave down from there. Now, we didn't get horizontal asymptotes. If I let x approach infinity, then that means f of x is approaching infinity. That means concave up the whole way, it'll never approach any horizontal line. And now, if I let x approach negative infinity, then I've got a negative infinity times e to the negative infinity. So, interesting. We need to figure out what that limit is. So we want the limit as x approaches negative infinity of x e to the negative, or x e to the x. Now notice, if I let x approach negative infinity, I have negative infinity times 0. That's an indeterminate form. So, it's time to put this in a fraction form. So we're going to make it, let's see, e to the x over 1 over x.